Many thanks. Thank you for braving the rain. And, thank you for the opportunity to talk. So the plan, I'm going to first discuss Cannon-Thurston maps, particularly in the setting of geometric group theory. And I'll tell you about Hydra groups, and then somehow I'm going to tie these things together. Okay, Cannon-Thurston maps. So let me start with Cannon-Thurston maps in the context that Cannon and Thurston first studied them. So suppose we take a surface of genus at least 2, and we cross it with an interval, and then glue the two boundary components together via a surface homeomorphism, well, more particularly a pseudo-Anosov homeomorphism. Doesn't matter exactly what that is, but we're going to get a hyperbolic 3-manifold. So we'll call that 3-manifold M, and we have its universal cover. Its hyperbolic 3-manifold. Its universal cover is hyperbolic 3-space, and the universal cover of the surface is sitting inside this, and it's naturally it's a copy of the hyperbolic 2-space. But how does it sit inside? Well, it sits in an exponentially distorted way. It's quite hard to picture how it sits. Here's a small attempt. This is a hyperbolic crochet by one of my Cornell colleagues, Dinah Taimina. And when I say this is sitting exponentially distorted, so think of the 3-ball model of hyperbolic 3-space, and you've got this copy of the hyperbolic plane sitting inside it, and exponentially distorted means it folds back on itself heavily, curls up, it's sort of scrunched up in there, sort of like that. Now, the boundary of the universal cover of the surface, the boundary of hyperbolic 2-space is a circle, and the boundary of hyperbolic 3-space is a 2-sphere. And so you might think that you get a map. So the inclusion here would induce a map on the boundaries. Okay, so, well, does it? And if so, what's it like? Okay, well, to make some of this a little more precise, I'm going to give you some definitions, but I'm going to do it in the context, in a sort of geometric group theory context. So I want to introduce hyperbolic spaces and hyperbolic groups in the sense of Gromov. Here's Misha Gromov. And he says that a geodesic space, that is a metric space in which every pair of points can be connected by a geodesic that's equal, that has length equal to the distance between the points. A geodesic space is hyperbolic when geodesic triangles are thin. More precisely, when there's a constant delta, there exists a delta greater than 0, such that for every geodesic triangle has the property that each side of the triangle is in a delta neighborhood of the union of the other two sides. So here's a geodesic triangle. We've got 3 points, and we join them up by geodesics. And for example, this side is in the union of the delta neighborhoods of this side and this side. That's the definition of being a delta hyperbolic space, and the space is hyperbolic when it's delta hyperbolic for some delta. Okay. So examples: hyperbolic plane, hyperbolic 3-space. An easy example is a tree, right? Because in a tree, what's a geodesic triangle? It's just a tripod, right? So in fact, every side of a geodesic triangle in this case is in a 0 neighborhood of the union of the other two sides, right? So it's 0 hyperbolic. So, most extreme example, most straightforward example. Okay, and one thing I want you to take away from this definition, one thing that's going to be very important to us, going forward, is what this means for geodesics emanating from a point. So if I've got a point, base point here, and I've got two geodesics emanating out, and I'll take some time t, so they're emanating out of this base point at unit speed, and so at some time t, look where they've got to. Well, if I join them up by geodesics, what I get a geodesic triangle, right? And because of this property that geodesic triangles are very close to being tripods, note that what happened as these geodesics progressed away from this base point is, at some point they diverge, and they just sort of go away from each other, and so you hit the tripod point roughly, and then just go in two separate directions. They diverge. Geodesic, yes, globally. Geodesic here means shortest path between yes, 2 points. Yeah, realizing the distance between them. Okay, so geodesics fellow travel for a while, and then geodesics emanating from one point fellow travel for a while, and then go their separate ways. And then we say that a finitely generated group is hyperbolic, or Gromov-hyperbolic, when its Cayley graph is hyperbolic. So some examples, well, a free group, the Cayley graph is a tree, so that's the easiest example. They're zero hyperbolic. And a surface group, genus 2. So here the Cayley graph naturally looks like the hyperbolic plane and is indeed hyperbolic. Okay. Now, what's the boundary? If we've got a geodesic hyperbolic space X and we take a base point E, then the boundary is it's equivalence classes of infinite geodesics emanating from the base point. And we say that two are equivalent when they stay a bounded distance apart. So gamma and gamma prime are equivalent when the distance between them is at most some constant for all time. Okay.
What's the quantification of the constant?
The constant depends on gamma and gamma prime, but not on t.
Why do we tell that it's a constant?
Yes. So if we've got 2 points in the boundary, so represented by a pair of geodesics, so I want to define a metric on this boundary. First, we need this notion. This is called the Gromov product, P dot Q, with respect to E. Oh, and I should say the boundary here doesn't depend on the base point. Anyway, P dot Q with respect to E is, roughly speaking, this is called the Gromov product, and it records how far these fellow travel. And then we can use that to define a metric on the boundary, the distance between P and Q. Roughly speaking, I'm brushing away some technicalities here, but this is the right way to think about this. Roughly speaking, it's e to the minus this distance. So that's to say that 2 points in the boundary are very close when geodesics geodesic representatives, geodesics going out to them, fellow travel for a very long way.
So you fix some delta distance apart, they have to be, or once they're beyond that distance apart, then they're no longer fellow travel.
That's right. That's right. So there's So if we're in a delta hyperbolic space, there's some constant I don't know, 10 delta, or I can't remember exactly what it is, which is as soon as the geodesics are more than 10 delta apart, they'll never come close again. They'll go off in opposite directions. And putting the space together with the boundary, we get a compactification. And then the Cannon-Thurston map. Yes, yes. So the neighborhood of a point of infinity. So you take the. Okay, you take. Well, first of all, I've given you the metric on the boundary, so that tells you what I mean by the neighborhood in the boundary. But how then do we extend that to x? Well, if you've got if you've got if you've got one point, if you've got a point in the boundary here, we've got a point. So there's the boundary and a point inside the space. Take a geodesic to that, and again, you've got a notion of closeness if these fellow travel for a long way, basically. Getting this all exactly right is a bit technical, but that's the idea.
So it's a metric space. The compactification is
I think so. I can't. Yeah, I don't. Yeah. Okay, so then. Well, it's how does what exactly depend? Right. It's okay. I'm suppressing a multiplicative constant in here. Exactly how that changes as you change delta, I can't exactly remember. And as stated, it's not strictly a metric, but to be more precise, there is some constant such you have one base. You have one base of the exponential on the left-hand side, one base on the other. Yeah, I can't remember exactly. But right. So the Cannon-Thurston map, so when we've got two hyperbolic spaces, x with its metric and y with its metric, but with y as a subspace of x and the base point sitting in y, we try to define the Cannon-Thurston map just in a naive way. If you've got a point in the boundary of y, which is the limit of points in y, we just try and map them to the limit of the same sequence in x. But this is troublesome potentially because the metrics on x and y are different. Right. The x has its own intrinsic metric, and y has its metric. So this is troublesome because there's no guarantee that this limit will exist. And indeed, if you had two sequences that approach the same point in the boundary here, even if their limits do exist, there's no guarantee that the limits will be the same here. That's the issue with this Cannon-Thurston map.
So just before that, how does the compactification
The boundary is a Cantor set, so it's tree with. Well, in the example I started with, the example that Thurston and Cannon studied, it turns out that this map, the map between the boundaries induced by the inclusion, is well defined. It's a map from the circle to the sphere, and it's surjective. In fact, it's a space-filling curve. It's a beautiful thing. So, and this has been generalized extensively in the context of Kleinian groups. There are lots of people involved, particularly Mitra. Recently, he's produced 2 papers. One was in the Annals last year. Second, I believe, is still a preprint. But together, they prove that the Cannon-Thurston map is well defined for all finitely generated subgroups of Kleinian, for all finitely generated Kleinian groups. So there's all finitely generated subgroups of the group of orientation preserving isomorphism isometries of H3. So this is in the context of Kleinian groups. The ambient space is H3, right? And we're just talking about we're talking about so you've got a discrete subgroup of the orientation preserving isometries, and that's what we're talking about the map on boundaries induced by inclusion there. So you've got you've got the group. The group is acting on H3. So take a base point and look at all the translates of the base point, and that's a map of the group into H3. Well, we then look at 2 metrics. Right, the group has the Cayley graph metric, and the ambient. Then you've got you're comparing that with the standard metric on H3. So then Mitra asked, how does this work in the geometric group theory context? So if you've got hyperbolic groups, H and G, is the Cannon-Thurston map always well defined? And if so, how does it behave? Okay. And the idea, when I was working on this, the idea is to take examples of hyperbolic groups, H a subgroup of G, such that H is heavily distorted in G. That is, such that the intrinsic metric on H is very different to the metric it inherits from the group G it's sitting inside. Because when there's no distortion, there's no issue here. Cannon-Thurston map is readily defined because there's very little difference between the metrics. So this question about limits existing and being well defined and all that doesn't really arise. Okay, so sources of these things. That brings me to section 2, Hydra groups. Okay, what are Hydra groups? Well, you remember Hydra is this beast that lived outside Linnea, and Hercules' second labor was to slay this thing. And it was a serpentine. It was a beast with multiple serpentine heads. And when Hercules, hacked off one of the heads, the trouble was that 2 heads would grow back in the place. And Hercules fought this thing successfully with the help of his nephew Iolaus, who Hercules knocked off a head, and Iolaus had this burning torch he pulled from the fire, and he would sear the stump so there would be no regrowth. But mathematically, that's not such an interesting solution to the problem. So I'm going to look at this from another perspective. For us, a hydra is just going to be, first of all, it's just going to be a word on 2 letters, A and B. Positive word. No, I'm not going to have any inverse letters. And Hercules is going to fight this by, first he knocks off the first letter. And then the hydra regenerates according to these rules. So every remaining A becomes an AB, and every remaining B stays as it is. And this repeats. So for example, against this hydra, what happens? Hercules knocks off the first B, that A produces a B. These two B's remain. That A produces a B. That B remains. And then, again, you knock off that A. These three B's stay as they are. That A produces a new B, and so on. And that's how it goes. And eventually, in this case, Hercules wins because this thing is destroyed, reduced to nothing. Okay. So he's victorious in 12 strikes here. Let's look at this systematically. Against a single A, he just kills that with one strike. Two A's, goes like that, 3 strikes. 3 A's, 7 strikes like that. A to the 4, 15. You can see the pattern. Against A to the n, he wins in 2 to the n minus 1 strikes. And in fact, he always wins. Yeah. You see. Nice exercise. Okay. Yeah, because just count the number of A's. Eventually, the number of A's always eventually goes down because in front of the first A is just B's, and he'll eventually get to the first A and then reduce the number of A's. In the meantime, lots more B's might appear, but the number of A's definitely goes down eventually. So it eventually goes to 0. So at that point, you've just got B's, and he kills that. Okay, let's develop this a bit further. 3 letters, A, B, and C. The regeneration is like this. A goes to AB, B goes to BC, and C goes to C. How does this play out? So against a single A, he just kills that with one hit. Against A squared, it goes like that. He knocks off the first A, and the second A produces a B. He knocks off that A, but that B then produces a C. He knocks off that B, and you just got a single C, which doesn't produce anything, and he kills that, and it's over in 4 strikes. Against A cubed, it goes like this. It takes a while, and he wins 46 strikes. A to the 4 goes like this. He wins. It takes that long. Okay, but he still always wins eventually. Same argument. But this, track the number of A's in front of the first A. You've just got B's and C's. But that's like what we saw before. He eventually kills that. On it goes. It's 4 letters: A, B, C, and D. Regeneration like this. A goes to AB, B goes to BC, C goes to CD, D goes to D. Against 1A, it kills that immediately. A squared goes like that. A cubed goes like this. He eventually wins, and it takes that long. Okay. Thank you for indulging me. This just amuses me. But he still always wins. What's going on here? Well, there's this family of fast-growing functions known as Ackermann functions, or Ackermann's function. And the family begins with n going to 2n. So to put that in the top row here, just if I give you some values. So you start with n goes to 2n. And then we define the subsequent functions using this recursion. So we'll start with them all being 1 at 0 apart from that one. So they're all 1s down there, and then you use this recursion to fill in the table like that. The point being, for example, the way this works, for example, is so this 16. You get this number 16. The recursion says, look 1 space to the left. That's 4. Go up 1 row and look at the entry for 4. It's 16. So that's what you put there. That's how this table builds up. And so this function is the doubling function. This is what you get. The next one is what you get by iterating that. You get n goes to 2n. Then you iterating that. You get a tower of 2's stacked n high, and then this one's iterating this somehow, and huge, monstrous, faster and faster growing functions. And so if we have more general Hydra with letters instead of A, B, C, we'll have A1, A2, and so on. And AI regenerates by becoming AI times AI minus 1, apart from A1, which is just fixed. Then we find that the number of strikes needed to kill AKN is growing like Ackermann's function. What we have is a sort of variation on this Ackermann effect, nested recursion. Okay. Yeah, it's not the right. It's not right. You need more. You need a bit more for that result. Yeah.
Faster than anything.
The diagonal is faster than A. Yeah. Yeah. So, but right, these functions are sort of extravagant, but they're not extravagant from the point of view of somebody studying recursion theory. But they are, the reason I'm telling you about them is this way they turn up as in terms of Hydra lends itself nicely to producing some interesting groups, and particularly some groups that are interesting in the context of negative and non-positive curvature. And so this is this family we call Hydra groups. So family GK generators A1 through to AK and T conjugates the A's, well, according to those regeneration rules. A1 is conjugated to A1, and AI to AI times AI minus 1. And theorem with Will Dyson about these things, well, it's got some nice properties. It's free bicyclic. Well, that's just how I've given it to you. So a free group semi-direct Z, the stable letter T generating the Z. So it's a one-related group. It's a cat0 group. I'll tell you more about this in a minute. So basically, it's very nice in some respects, and yet it's got a subgroup HK, specifically the subgroup generated by A1T, A2T, and so on through to AKT, which is free of rank K, also very nice. Except it sits in here. Its distortion is like the kth Ackermann function. I'll tell you precisely what this means in a minute. So let me just go through these again. Free bicyclic, that's just how I've given it to you. It's a free group on A1 through T, semi-direct Z which is generated by this T, and this is how the semi-direct product works. This is describing a free group automorphism. It's a one-related group. Well, that means it can be presented with a single defining relation. Well, that's not how I've given it to you here. But if I rewrite these relations as, well, this says that the first one says that A1 and T commute, and this family says that AI minus 1 is this commutator. And I can use these to eliminate all of the AIs apart from which way round is it? Apart from AK. So I first eliminate A1 and then A2 and so on, and I get this group as a one-related group, this sort of angle relation here. So it's a one-related group, so it's very nice in that respect. And you can actually, this is going to be useful in a moment. We can rewrite this relation. If we let S be T inverse, you can rewrite it like this. So this means take S, conjugate by A, and then take S and conjugate by that, and then take S and conjugate by what you've got so far, and so on, and do this K times. That should equal S. Just a general thing, when you've got a finally presented group, we can build the presentation 2 complex. This is the natural 2 complex associated with the presentation. You get this by, so it's the beginning of the construction of an Eilenberg-MacLane space. You start with a single vertex. You have a loop, one loop for each of the generators, and direct them, and then attach cells, one for each defining relation, using the relations to give you the attaching maps. So you get a little finite 2 complex whose fundamental group is the group presented like by this, and its universal cover is called the Cayley 2 complex, and the one skeleton of that is the Cayley graph. Okay, now to say that this group's cat0, well, that is to say that that's a sort of, it's another Gromov definition. It's to say it's non-positively curved. It means it acts geometrically, it acts in a nice way on a space that is non-positively curved in the sense that triangles are no fatter than Euclidean triangles. How do we prove that this group's cat 0? How do we see it? Well, you can unravel this presentation by introducing, this can be rewritten as this. So alpha 1 is everything above this S, and then anyway, it doesn't matter. You can unravel it to this presentation, and we can, at least in the case of say of G1 and G2, you can probably see that this is non-positively curved. So G1, you just have alpha 1 and S, and they commute, and the Cayley 2 complex would just be a plane tessellated by squares coming from this defining relation, right? And then when we go to G2, we introduce alpha 2. We've got one more relation that says that alpha 2 conjugates S to alpha 1. Well, that gives, in the Cayley 2 complex, that gives these sort of corridors of cells. So these get square. These also give squares, and these squares tell us that alpha 2 conjugates S to alpha 1. So in the Cayley 2 complex, you get planes that come from alpha 1 and S, and you have these corridors from this relation that join planes. And so this is a line of S's, and this corridor is joining it to a line of alpha 1s. So you've got planes stacked up, but with a 90-degree twist. And this is just a small part of the Cayley 2 complex. You've got these corridors coming off every line of S's here, So we've got a tree-like arrangement of planes with 90-degree twists. Anyway, maybe you can convince yourself that that's a non-positively curved thing, but that's a bit mind-bending, and you're in a bit of trouble. I am anyway, visualizing what's going on when we increase k. Can you really convince yourself that this is non-positively curved? Happily, there's a nice way of just checking. It's called the link condition. So in this Cayley 2 complex, imagine a very small sphere around a vertex, any vertex. All vertices are the same. Because it's a 2 complex, this small sphere slices through the complex to give us a graph. That's called the link of the vertex. And this is what the link looks like for GK. This is what this graph looks like. And what's the obstruction? The link condition, there's an obstruction to being non-positively curved. It tells you that this 2 complex is non-positively curved if and only if there's you don't want at the vertex, you don't want cells coming together to give you positive curvature. So imagine this link graph. Metrize the edges so that the lengths of the edges correspond to the angles in the cells. Right? You've got this. You're slicing through cells, and call the lengths of the edges the angles you're cutting through. So we're just working with squares. So all the angles are 90 degrees, pi by 2. So every edge is labeled pi by 2, and the condition is simply that there are no simple loops of total length less than 2 pi. You don't want to get any positive curvature appearing anywhere, and so you just draw the graph and stare at it and check. There's no. So that's the link condition. So that tells us we get something cat 0. Why do we get huge distortion? Well, this is where the Hydra thing comes in. So let me demonstrate it in the case of G2. So here's G2 just in terms of A's and B's, and here's this interesting subgroup H2 generated by AT and BT. this is called a Van Kampen diagram. So this is a graphical representation of the fact that in this group, so consider all red edges, all horizontal edges, red edges labeled by A's, and all horizontal green edges as labeled by B's, and all vertical edges as labeled by T's. So this diagram says that a to the 4 times t to the 15 equals AT, AT, BT, AT, BT, 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 AT, BT, 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 down to that, right? So it, because these cells correspond to defining relations, right? The blue ones correspond to the T commuting with B, and the orange ones are pentagonal and tell you that they correspond to this relation. So this shows how it follows from these relations that you get this equality. And if you look at the words you could read along the horizontal edges here, well, here's what they are. A to the 4 along the top, AB, AB, AB along the second row, BA, BB, and so on along the third row. What we have here is precisely this Hercules fighting the Hydra thing playing out. Okay, so now take this and put another line of cells on it, and then put another corridor of cells on it, and then put the mirror image over there. And what we've then got is a to the 5 times TB times a to the minus 5 equals some word on the generators of H2, some word on AT and BT. And this, right, so, and if this has length n, if I'm generalizing this to the analogous calculation in an arbitrary GK, not just G2, then we're getting a word of length n, or 2 or 2n plus 2, roughly n, equaling a word on the generators of HK of length given by Ackermann's function, right? Given by because this, the length along here is the duration of that battle that Hercules fought. Okay, so and this is where we're seeing the huge distortion, because the word you read along the top from here to here in GK it's got length n, and in the subgroup it's got this length. It's it's enormous, and you can't find a shorter word on the generators of the subgroup that represents the same group element, because, well, first of all, notice actually this is a reduced word along the bottom on the generators of the subgroup, and I told you actually that this subgroup is free. I didn't prove that. It's a bit painful to prove, but it's true, and it follows that there's no other word that represents the same group element. Right. So this is why we're saying this is enormous distortion. This is distortion like Ackermann's function. Okay. So then we could ask, is there an analog of Cannon-Thurston's theorem for these Hydra groups, for these HK sitting in GKs? But this is actually problematic because these aren't hyperbolic. No, they're non-positively curved. They're cat 0, but they're not hyperbolic. They're not hyperbolic because, well, really because of this relation. This is T commuting with A1. There's a Z cross Z subgroup inside GK, and that's an obstruction to being hyperbolic. So these aren't hyperbolic, but we can hype up these examples to turn them into hyperbolic ones. We can build more elaborate free bicyclic groups. So some free bicyclic groups F. I'm not going to take you through all the details, but something the same as before with the A's, except slightly. I've introduced an A0 as well, and then I've introduced some B's, which is sort of noise or junk, which gets thrown in, and So this is the purple stuff is sort of like before, but the red stuff is junk that messes, interferes with that Z cross Z subgroup. It puts some noise into that Z cross Z subgroup, cures that problem, but it does so in a way that holds on to this huge distortion effect. So you would get the same pictures for distortion, but lots of this noise comes into the distortion words. But basically the same story works. Is it what? I'm not sure, because we go at, so I haven't actually, I'm about to explain to you why we actually get a hyperbolic group. So we take a very different approach to checking. Which is this. So what we do is so this is with Will Dyson and Noel Brady. What we did was we built these more elaborate free bicyclic groups. So the original Hydra, I described how they were cat zero. You change the presentation somehow, and the presentation 2 complex is non-positively curved. You do the same thing here. You change the presentation, you get a cat zero presentation, and this describes the cat zero presentation. So this is called these are called labeled. This is an encoding of the presentation. So all the symbols you see are generators, and an edge, say here from S hat to beta 6, an edge labeled by beta 5. That says that beta 5 conjugates S hat to beta 6. So you've got lots of length 4 relations plus a couple of anomalous relations, and you can build your Cayley 2 complex for this, and you can look at the link. There it is, and you check that it is cat 0 first of all by checking the link condition. But we want more than that. We want that we get a hyperbolic group. And it turns out there's a theorem called the flat plane theorem that allows us just to check we've got a hyperbolic group by referring to this graph. And the theorem says that proper co-compact cat 0 space is hyperbolic if and only if there's no subspace isometric to the Euclidean plane. That's something we can check by staring at this graph, because how could we get a Euclidean plane in the Cayley 2 complex? Well, it would have to be tiled by cells that come from somehow, and at each vertex you've got to have angle 2 pi because you're tiling the plane. Well, so you can look in here for simple loops of length 2 pi that would correspond to these that could correspond to vertices in this tiling of the plane. There are some, they exist, but then these cells have other vertices, and they must also have angle 2 pi around them. But you can check that always fails. All the cells that have the potential to sit inside flat planes have these poisoned corners where the angles all go wrong. So so there's no flat plane, so we get a hyperbolic group. Okay.
So what you say, somehow if you look at the link, that's not for your previous one, but it's your standard, it's like just minus.
No, it's still you're still looking at a tiny sphere. You're still looking at the link, but
The argument we gave is something.
I see what you mean.
Where you stand, not just
Right.
then you see just negative curvature.
I see. Yeah, I suppose that's right. I'm not sure how to make it precise, but I see the intuition. Yeah. Okay. So now, so these hyperbolic Hydra. What can we say about the Cannon-Thurston maps? Well, turns out they are well defined, despite the crazy distortion. They are well defined. They're not counterexamples to Mitra's question. but nonetheless, do we get, you know, all that effort to get getting crazy distortion? What does it buy us? And it shows up. It shows up in strange properties of the metric properties of the Cannon-Thurston map. So, you know, you see it in the modulus of continuity of the map. So, if you've got a map between metric spaces, f mu to v, and this is the modulus of continuity. It sort of just compares epsilon and delta in the definition of continuity. It's the supremum. Look at all pairs of points in U, the distance most delta apart, and see how far apart their images can be. And well, it turns out that for these hyperbolic hydra, the Cannon-Thurston maps exist, but their modulus of continuity is crazy in this sense. I've suppressed constants to make this palatable, but it's roughly so modulus of continuity is interesting when you feed in small values of delta, and this says that you get this being bigger than 1 over n, feeding in absolutely minuscule things on the left-hand side, 1 over an Ackermann function. And the reason for that, this is actually a general thing about when you've got a heavily distorted subgroup of a heavily distorted hyperbolic subgroup of a hyperbolic group. The reason is, so we've got, here's the base point, mapping to, here's the base point in H. You imagine it mapping into G. So H is a hyperbolic subgroup of a hyperbolic group G. So E is going to E, and we've got huge distortions. So there are some points that are, so for these hyperbolic hydra, there are some points where you've got the distance, this point to E is like AK of n, but it maps to a point a distance n away. If we take 2 points in the boundary represented by a pair of geodesics that travel out to, they go close to this point, and then they diverge roughly there and go off to the boundary. We map those, you know, we map over to G and look at where those boundary points go. The Cannon-Thurston map's well defined; they go somewhere, but geodesics out to them go close to. They travel together roughly out to here and then diverge. So so this is traveling together for a very long way. So these points are very close in the boundary. This is traveling together comparatively short distance, so these aren't so close. So that's where this is coming from. Okay. I believe in everything until it's disproved. So I believe in fairies, the myths, dragons. Anybody know who said that? It was John Lennon. Anticipating what is known as Gromov's thesis. That is, in the context of finitely generated or finitely presented groups, that is basically that anything goes in finitely presented groups unless there's a fairly easy, obvious reason it doesn't. Anything goes, it might be very painful and hard to prove what craziness you think exists, does exist, but anything goes. And so again, working with Owen Baker, we did eventually prove there are examples of hyperbolic groups where there's no, with hyperbolic subgroups where there's no Cannon-Thurston map, where the Cannon-Thurston map fails to be well defined. Okay, so how do we go about this? Well, here are the groups, or here's the basic example. We've got a group G. Here are 6 generators, and here are the relations. So the commutator of A and B is some word C. So the C's are positive words on the capital C's are positive words on the little c's, and the capital D's are some positive words on D1 and D2. And we can choose these in such a way that we get a hyperbolic group. The subgroup H, generated by B, D1 and D2, is free of rank 3. But the Cannon-Thurston map from the boundary of H to the boundary of G fails to be well defined. What's the idea? Well, the idea is we find a pair. Here's H. Here's the base point. We find a pair of sequences in H that limit to the same, that tend to the same point in the boundary. But the idea is that they're going to limit to different points in the boundary of G. That is to say that so the condition for them to limit to the same point in here in H is look at geodesics from the base point out to Pn and Qn, see how far they fellow travel. Well, as n goes to infinity, that distance should go to infinity. That's what it means for them to converge to the same point. Over here, we're going to have, if we draw geodesics between Pn and Qn, it's actually going to go right back to the base point and out again. So geodesics, so geodesics going from E to Pn and Qn in the metric on G, in G, they don't fellow travel at all. They immediately go their separate ways. So that implies that these are different points in the boundary. That the Pn and Qn limit to different points in the boundary. How do we make this happen? Well, here are some paths in the Cayley graph of this group. So here's the base point, E, the identity. Qn will position it at b to the n, and Pn will position over here at a to the minus n d1 inverse a to the n b to the n. And it turns out that in this group, the group element that takes you from Pn to Qn, in other words, b to the minus n, a to the minus n, d1, a to the n, b to the n, equals a word on d1 and d2, a positive word. In fact, it's a positive word of length double exponential in n. And I said that H, the subgroup generated by B, D1 and D2, is free, rank 3, and so so if you want to go from Pn, suppose we're at the base point E and we're in H and we want to go on geodesics out to Pn and Qn. Well, the Cayley graph of the free group is a tree and is sitting inside the Cayley graph of G here. And so the journeys from E to Pn and Qn, well, they go via Qn. You go out to Qn, that one GD that's got to Qn, the other one continues along here to Pn. So they fellow travel for this distance, along this b to the n. They fellow travel for a distance n, which tends to infinity as n goes to infinity. But if you're in the ambient group G, you can the geodesics from E to Pn and Qn go, well, this one to Qn you go along here, but to Pn you go this way. Right. So they immediately, and it turns out this path along the bottom is a geodesic in G. So it goes right through E. So this happens. And the tools that make this work, it's really small cancellation theory, which is a sort of theory of hyperbolicity through the combinatorics of words with very little overlap. And we use Rips words to these Cs. They're a bit like the noise words that were thrown into the Hyperbolic Hydra. They're words that that don't have much overlap, and there's a family of words due to rips that are convenient to use in this context. Okay, just to finish, there's one loose end here, I think. I mentioned a moment ago that the word on D's I was talking about a moment ago was doubly exponentially long as a function of n. And correspondingly, the subgroup H in G on the previous slide is double exponentially distorted. Now, in the Kleinian groups context, well, the Kleinian groups context is a bit different, but it seems that the examples that correspond to these geometric group theory setting examples, they're all exponentially distorted or not distorted at all. So here's an open question. Is the Cannon-Thurston map well defined necessarily for exponentially distorted subgroups of hyperbolic groups? Exponentially distorted hyperbolic subgroups of hyperbolic groups, I should say. If you've got subgroups, hyperbolic subgroups of hyperbolic groups can be, or any subgroups of hyperbolic groups can be undistorted, but if they're distorted, then it turns out the distortion has to be at least exponential. So this is the minimal distortion. If you're going to be distorted, then this is the minimal possible distortion. We still don't know whether this always gives rise to Cannon-Thurston maps. It would be nice to know, because it would render a lot of the work on Kleinian groups just a question about hyperbolic groups and a question of geometric group theory. Okay, I'll stop there.